If you haven't viewed Jupiter through a small telescope, you should. There you'll see another world and small dots of light that are the moons of Jupiter. Those dots of light remain just that until we sent spacecraft to go investigate. I really liked the Galileo mission to the Jovian system. The 2 Voyager missions opened the door to Jupiter, but Galileo moved in and stayed a while, getting to know the place the same as you would learn a new city that you just moved to. So please take a few minutes and follow the long road traveled and the many discoveries of the Galileo mission to the Jupiter system. You know, it's amazing that the Jupiter Orbiter mission made it to the launch pad at all. The Jupiter Orbiter Probe project received congressional approval on 1 October 1977. NASA's plan was to build and launch the Jupiter Orbiter Probe mission by 1982. The JOP was to be transported up to Earth orbit by the Space Shuttle, then propelled onto a direct Earth-Jupiter trajectory by means of a solid-fueled inertial upper stage launch system. The JOP would reach Jupiter in 1984. In 1978, the JOP project is renamed Galileo. Named after the first scientist, Galileo Galilei, he discovered the 4 large Galilean moons, the first objects found to orbit another planet. Very quickly, the need for a heavier spacecraft is identified. For the 1982 launch, NASA developed a Mars gravity assist trajectory to conserve fuel. But the Galileo team had concerns over the shuttle's engines being rated to 109% to achieve the heavy lift needed to launch the now heavier Galileo. The use of the more powerful liquid-fueled Centaur upper stage instead of the IUS is considered, but NASA Administrator Dr. Robert A. Frosch opposed the use of the Centaur due to safety concerns. To solve Galileo's weight problems, NASA announced plans to separate the orbiter and probe mission and sets 1984 launch dates. But due to the cost of the extra probe launch and the cost overruns on Boeing's IUS, the orbiter and probe are recombined into one mission using a wide-body Centaur and postponing the launch until April of 1985. In early 1981, the new Reagan administration's Office of Management and Budget Director, David Stockman, proposes budget cuts, which, if approved by Congress, could force the elimination of the Galileo mission, other future deep space projects, and even JPL. But Senator Strom Thurmond and the Department of Defense both backed the Galileo project for its military benefits. Senator Thurmond informed OMB Director Stockman that the Air Force needed satellites with a survivable autonomous capability to remain operational during times of war if communications with the satellites was lost. In fact, JPL had already developed and applied autonomous technology for the Air Force in parallel with the Galileo spacecraft's development. At the end of 1981, OMB Director Stockman agreed to reinstate Galileo back into the fiscal year 1983 budget, but recommended that Centaur development be killed. This change was solely driven by budget pressures. NASA restructured Galileo for a mission without Centaur, making plans to use Boeing's solid-fueled IUS augmented with a solid-fueled kick stage for increased propulsion. The launch, scheduled for August 1985, would use an Earth gravity assist to reach Jupiter by 1990. Even as NASA made plans to use the lower-powered IUS, Centaur still had strong support for use as a space shuttle transfer stage. In July 1982, President Reagan signed a bill directing NASA to design, develop, and procure the Centaur upper stage and to stop work on the IUS for Galileo. NASA delayed Galileo's launch for another year until May 1986. Now that the Centaur question was finally answered, JPL set to work to meet the 1986 launch date. For the next several years, the challenges became more technical and management-oriented than political. At 3 a.m. on December 19, 1985, Galileo began the first 3,000-mile leg of its half-billion-mile journey to Jupiter. Galileo's management was concerned that the plutonium that powered the spacecraft would draw anti-nuclear protesters, or worse, a terrorist attack. The caravan crossed America without incident or mishap, reaching the Kennedy Space Center on the 23rd of December, 1985. Ahead lay the integration of Galileo with Centaur and other final tests. In late January 1986, Galileo was tanked up with hypergolic propellant, a very hazardous process, but Galileo passed the test. A few days later, on the morning of January 28, 1986, the Space Shuttle Challenger and her crew of 7 was lost. It was very clear to all of the Galileo team that the mission to Jupiter was on hold or may never be launched. No firm launch date could be set until after the Rogers Commission made its report to President Reagan in June of 1986.
This has been a difficult passage for America, but we will go on, just as the crew of the Space Shuttle Challenger would have wanted us to. We'll use every ounce of American skill, ingenuity, and gumption, and we'll work twice as hard and be twice as vigilant. We'll simply do what has to be done to make our space program safe and reliable and a renewed source of pride to our nation. America has a claim to stake on the future. We've suffered a tragedy and a setback, but we'll forge ahead, wiser this time and undaunted as the spirit of the Challenger and her 7 heroes.
NASA's view was that it would take until early 1988 for the shuttles to fly again, and Galileo would probably have to wait longer depending on where it ended up on the flight priority list. Also, in June of 1986, NASA canceled the Shuttle Centaur program. This forced Galileo to use the lower-powered IUS, solid fuel booster. JPL had anticipated that Centaur might be scrapped and had already initiated a series of alternative launch plans for Galileo. Without Centaur, a direct flight to Jupiter was impossible. Given the spacecraft's propellant capacity, only the Venus-Earth-Earth trajectory would work, and that flight path would take 6 years to arrive at Jupiter. Galileo was designed to operate at distances between 1 to 5 astronomical units from the Sun. The Venus-Earth-Earth gravity assist trajectory would bring Galileo as close as 0.7 AU from the Sun, encountering twice the solar radiation intensity as that found near Earth. Also, with a 6-year trip versus the 2-year trip via Centaur, the plutonium in Galileo's RTGs would decay more than planned, thus reducing their power output once Galileo arrived at Jupiter. The spacecraft sent to the Kennedy Space Center in April of 1989 was very different from what had been sent there 3+ years before. New software and substantial thermal protection changes were made. There were also large improvements made in equipment reliability due to the longer mission time via the Venus-Earth-Earth gravity assist trajectory.
Coming up next on C-SPAN, a news conference by the Christic Institute, the Foundation on Economic Trends, and the Florida Coalition for Peace and Justice. They announce a lawsuit attempting to halt a manned NASA space launch. The lawsuit is aimed at the launch of the Jupiter probe Galileo aboard the shuttle Atlantis, scheduled for October 12th.
The courts threw out the lawsuit. Galileo was finally launched on October 18, 1989, by the Space Shuttle Atlantis on the STS-34 mission.
And about this time, I turned to look at Don, and I said, "You didn't prepare me for this," as the tower went by a great deal faster than I thought it would, based on my simulator experience. $4.5 million pounds or so of machinery and 6.5 or so million pounds of thrust. The roll maneuver. There was a great deal more vibration here than I expected, and I think it's probably acoustic. It shakes your body and your soul. The main engines throttle back, and as you reach maximum dynamic pressure, and there's some very good shots here of the waves created by the speed and the maximum dynamic pressure as we went through the area of max Q. SRB SEP, this is another area that Don failed to prepare me well for. In the simulator, there's a flash bulb or something that goes off when you get to SRB SEP, and in the real life, there's an explosion that goes off right in front of your face. It was wonderful, but it was surprising.
And get ready to launch the IUS. The first thing, a visual thing that we had to do was get the IUS up to 28 degrees, and that all went very smooth. The deploy time came, we flipped the switch, we deployed it, and it slowly went out of the payload bay. And at that time, both Ellen and I sighed a great sigh of relief, because we figured Galileo was not our concern at that point. And then Don was getting ready to fly the shuttle and maneuver it away from the IUS and Galileo stack.
1 hour later, when Atlantis had flown to a safe distance, the IUS rocket fired, speeding Galileo into interplanetary space and onto its first objective, Venus. The Venus-Earth-Earth gravity assist trajectory presented new scientific opportunities for Galileo. During the 6-year flight to Jupiter, the spacecraft would pass close to Venus, Earth, and the Moon. Flying through the asteroid belt twice would allow Galileo to make close observations of at least 3 asteroids: Bosania, Gaspra, and Ida. Unlike previous planetary spacecraft, Galileo was designed with a dual spin feature. Part of Galileo rotated continuously at 3 RPM, which accommodated the field and particles experiments. The despun section of Galileo remained stationary, providing a fixed orientation for imaging equipment and other sensors. On the way to Venus, 2 trajectory correction maneuvers were performed. A third TCM was not needed because the aim point at Venus was virtually perfect. Data collected at Venus was stored on a tape recorder. The high-gain antenna remained stored and folded up like an umbrella. Keeping the high-gain antenna shaded and cool prevented the optimum orientations for data collection. The data would be transmitted with the 2 low-gain antennas when near Earth. 1 large and some smaller TCMs put Galileo on a precise path for an Earth flyby and gravity assist. This would be the first time that interplanetary spacecraft had returned to Earth, even if briefly. Galileo was able to provide new and unusual views of parts of the Moon. Images from Galileo proved that a huge impact basin did exist on the far side southern section. The 1,200-mile across basin was formed by a 100-mile wide meteor that struck the Moon's surface. It probably hit so hard that the Moon wobbled and lurched while it blew out a large chunk of the Moon into space. Astronomer Carl Sagan pondered, could life on Earth be easily detected from space? He devised experiments for Galileo to perform on this first ever flyby of Earth by a deep space probe. Galileo found the Sagan criteria for life: the absorption of red light due to photosynthesis, oxygen production as a result of plant activity, high levels of methane that would break down with oxygen present, and modulated narrow band radio transmissions that could not be from any known natural source. Galileo's experiments were to become future controls in the search for life on exosolar planets that would not be discovered until the middle 1990s. With Earth in the rear-view mirror, Galileo treks out into the asteroid belt and the Gaspra encounter. On the 11th of April 1991, commands were radioed to open Galileo's high-gain antenna. The motors turned on, but the expected signal confirming that the antenna had opened never came. JPL formed a high-gain antenna deployment anomaly team to review and study the problem, as the low-gain antennas were adequate, for the time being, to transmit data back to Earth. On October 29, 1991, Galileo became the first spacecraft to encounter an asteroid. Discovered in 1916, 951 Gaspra is one of the 5,000 objects in the main asteroid belt, a donut-shaped area midway between Mars and Jupiter. Galileo passed approximately 1,600 kilometers from Gaspra at a relative speed of 8 kilometers per second. Images revealed Gaspra to have a cratered surface and an irregular shape. At 20 kilometers long, 12 kilometers wide, and 11 kilometers thick, Gaspra is tiny compared to the largest asteroids. Gaspra's irregular shape suggests that it was broken off a larger body through catastrophic collisions. In December of 1991, Galileo would be the farthest it would get from the Sun for several years. NASA managers believed that the December cooling opportunity would provide the best chance to free the crucial high-gain antenna. After many hours of cooling, data sent from Galileo indicated that the attempt had not worked. NASA continued the thermal cycling attempts over the next several months with no success in freeing the high-gain antenna. Returning to Earth 2 years after its last Earth encounter, Galileo discovered a wealth of information about the Earth's geocorona, the outermost part of Earth's atmosphere. The diffuse hydrogen gas of the geocorona is forced in an anti-sun direction, creating a geotail extending 400,000 kilometers away from Earth. Galileo was able to image the northern polar region of the Moon in infrared and visible light, providing new data on lunar geological processes. Galileo also investigated a series of high stratospheric ice clouds over Antarctica. On December 8, 1992, Galileo once more flew by Earth, passing within 300 kilometers above the South Atlantic, finally putting Galileo on a direct trajectory to Jupiter and the encounter with asteroid 243 Ida. With Galileo closest to the Sun that it would ever be again, controllers ramped up their efforts to deploy the stuck high-gain antenna. Unfortunately, after all their efforts, NASA had to accept that the high-gain antenna would not release, and that the mission would have to continue on with the slower data transmission rate of the low-gain antennas. In spite of the LGA's slow transmission rate, project staff devised ways to complete 70% of the mission's scientific goals by squeezing more data into fewer computer bits with data compression. And dependable data storage aboard Galileo took on a new importance. Also, the Galileo team augmented data flow by improving the ground antenna systems of the Earth Deep Space Network. The Galileo high-gain antenna workarounds would end up becoming especially useful for the faster, better, and cheaper interplanetary missions of the future. On August 28, 1993, Galileo flew within 2,400 kilometers of asteroid 243 Ida. Ida is considerably larger than Gaspra, but is also highly irregular, measuring 56 by 24 by 21 kilometers. Like Gaspra, Ida is heavily cratered. Ida's cratering is more extensive than Gaspra's, suggesting that Ida formed earlier than Gaspra. Months after the Ida flyby, when Galileo's images were played back, Ida was discovered to have a small moon, which would be named Dactyl. Approximately 1.6 kilometers in diameter, Dactyl orbits about 100 kilometers from Ida's center. This was the first conclusive evidence that asteroids could have satellites. With Galileo's planetary gravity assist and asteroid flybys now completed, the spacecraft continues on to arrive at Jupiter on December 7, 1995. On March 24, 1993, world-class comet seekers Eugene and Carolyn Shoemaker and David Levy discovered a comet orbiting Jupiter. This comet was in the unusual form of a line of numerous pieces resembling a string of pearls. Further analysis showed that in July of 1994, the comet, now called Shoemaker-Levy 9, would smash into Jupiter. When this happened, Galileo, though still far away, would have an excellent view of the collision sites. The comet's fragments would hit Jupiter's night side away from the Sun. Because of this, Earth-based telescopes would not be able to observe the impact sites directly, but Galileo could. From the 16th through the 22nd of July 1994, 21 pieces of Comet Shoemaker-Levy 9 collided with Jupiter in an event that was spectacular and beyond expectations. The first comet fragment hit Jupiter at over 320,000 kilometers per hour, and it generated an intensely bright fireball at least 3,000 kilometers high. These impacts also resulted in hot bubbles of gas in Jupiter's atmosphere. They also left large, dark, scar-like spots that persisted for weeks. Some of those spots were 2 to 3 times the size of the Earth. The Shoemaker-Levy 9 event was the first collision of 2 solar system bodies ever observed, and fate gave Galileo a front row seat. On July 12, 1995, Galileo released its 750-pound Jupiter atmospheric probe. The spacecraft was 83 million kilometers and 5 months away from Jupiter at the time. In December 1995, the probe would become the first Earth emissary to plunge into the atmosphere of one of the solar system's gas giant planets. On July 27, 1995, 2 weeks after the probe release, Galileo fired its main engine for 5 minutes and 8 seconds, performing an important maneuver that would deflect it away from a collision course with Jupiter. This was the first burn of Galileo's engine, and it demonstrated the engine's operability. Firing the engine had to wait until the probe's release because the probe had been mounted in front of the engine. This maneuver was enough for Galileo to miss Jupiter by 230,000 kilometers. This would allow Galileo to fly overhead and receive data from the probe as it fell through the Jovian atmosphere. Galileo would then relay the stored data back to Earth. In August 1995, 63 million kilometers from Jupiter, Galileo observed one of the most intense interplanetary dust storms measured. Io's volcanoes appeared to be the source of the dust hitting Galileo's dust detector. In October 1995, Galileo's reel-to-reel tape recorder would not stop rewinding. A failure of the recorder, in addition to the failed to deploy high-gain antenna, would doom Galileo's mission. Project staff restored the recorder, but with less data storage space. This forced the cancellation of the close-up photos of Europa and Io to to be taken during Galileo's arrival at Jupiter. A tough call, but NASA could not risk losing the atmospheric probe's data. By the end of November 1995, Galileo had completely passed Jupiter's bow shock 9 million kilometers from Jupiter, and finally into Jupiter space. Galileo now began its first direct measurements of the Jupiter system. December 7th, 1995, arrival day. The next 24 hours would be the most eventful and busiest of the whole mission. The first major event was the flyby of Europa at 32,500 kilometers. Next, Galileo flew by Io at only 890 kilometers above the volcanic moon. 6 hours before atmospheric entry, an internal alarm woke up the probe and turned on its instruments to begin warming them up. 3 hours before entry, when the probe passed between Jupiter's ring and the upper atmosphere, the probe's energetic particle instrument detected a belt of radiation 10 times stronger than Earth's Van Allen belts. The probe sped by Jupiter's cloud tops on its way down into the planet's atmosphere. As the probe entered the atmosphere, it experienced rapid deceleration and intense heating of the gases near the probe. At entry plus 55 seconds, the probe experienced peak aerodynamic stresses and a maximum force of up to 250 Gs. At entry plus 172 seconds, the pilot parachute deployed, followed very quickly by the aft heat shield separating and pulling the main parachute out. The main parachute slows the descent module. Then 3 explosive separation bolts fired, and the forward heat shield fell away. At entry plus 3.8 minutes, the orbiter locks on to the probe's signal. At entry plus 6.4 minutes, zero altitude is attained. Zero altitude is defined as the point where the pressure is equal to 1 bar, or Earth's surface pressure. Data collected by the probe caused scientists to revisit many of their beliefs about the formation of Jupiter and the rest of the gas giants in our solar system. The probe's measurements of Jupiter's atmospheric composition, wind velocities, temperatures, cloud characteristics, electrical storms, and elemental and molecular abundances painted a very different picture of Jupiter from what was expected. The most puzzling of the probe's findings was the virtual absence of water and water clouds. Also, the probe's lightning and radio detector found no lightning in the vicinity. The most accepted theory for these findings was that the probe entered into an atypical entry site comparable to the Earth's desert regions. At entry plus 61.4 minutes, the probe's signal was no longer detected. After completing its mission, the probe was slowly destroyed by the increasing heat and pressure, becoming one with the atmosphere of Jupiter. After receiving the data from the atmospheric probe, Galileo had to fire its 400-Newton engine to slow itself down relative to Jupiter and allow the giant planet's gravitational field to capture it. The orbiter's 49-minute burn reduced its velocity by over 600 meters per second until the orbiter was finally captured. Now, in Jupiter orbit, Galileo became the first artificial satellite of the Jovian system. During most of Galileo's elongated, elliptical 7-month-long initial orbit, the spacecraft slowly transmitted data to Earth that had been received from the atmospheric probe and stored on its tape recorder. On March 14, 1996, Galileo approached apogee, or its furthest point from Jupiter, and fired its main engine once again. This changed the craft's trajectory so that its perigee, or closest point to Jupiter, was raised from 4 Jupiter radii to 10 Jupiter radii. which would reduce Galileo's radiation exposure near Jupiter. Each orbit of Jupiter usually included a close encounter with one of Jupiter's satellites and a cruise period that typically lasted a couple of months. During each encounter, data was collected at high rates and stored on the tape recorder due to the transmission limitations of the low-gain antenna. These cruise periods gave the spacecraft the chance to send data to Earth, as well as to take additional fields and particles measurements that were sent to Earth in real time. The first close encounter of its prime mission, G1, was with Ganymede on June 27, 1996, at an altitude of 835 kilometers. This encounter reduced Galileo's orbital period from 210 to 72 days, which allowed more orbits and close encounters each year. A radio science experiment analyzed Ganymede's gravitational field and internal structure. Galileo's instruments detected evidence of a self-generated magnetosphere around the Moon. On September 6, 1996, encounter G2 passed 260 kilometers near Ganymede's pole. This gravity assist put Galileo into a coplanar orbit with the other Galilean satellites, permitting subsequent encounters with them. G1 and G2 radio science and other data revealed that Ganymede has an interior that is probably differentiated into a core and a mantle. On November 4, 1996, Galileo performed its first flyby of Callisto, encounter C3, at 1,136 kilometers. Observations supported the theory that Callisto has a homogeneous internal structure which is 60% rock and 40% ice. Galileo's first close encounter with Europa, E4, occurred on December 19, 1996. The spacecraft flew as close as 692 kilometers above Europa's surface. The return of data from encounter E4 was limited by a solar conjunction that peaked on January 19, 1997. Due to the Sun's interference with Galileo's radio transmissions, there was no close encounter with a Jovian moon during the J5 orbit. Europa encounter E6 took place on February 20, 1997, at an altitude of 586 kilometers. The main scientific objective was to conduct high-resolution coverage of Europa. Monitoring of Io was also conducted during orbit E6. The spacecraft would fly as close as 400,000 kilometers to Io. Radio science occultation measurements provided data on atmospheric profiles of the moons, Jupiter, and also Europa's gravitational field. Ganymede encounter G7 was on April 5, 1997. Galileo passed by the Moon at 3,102 kilometers. Flying over the high latitudes, taking high-resolution observations of high-energy impact regions, as well as Jupiter magnetosphere and aurora observations. Ganymede encounter G8 occurred on May 7, 1997. Galileo passed over Ganymede's mid-latitudes at 1,603 kilometers, allowing new terrain to be imaged. Callisto encounter C9 happened on June 25, 1997. Galileo passed over the Moon at 418 kilometers. Analysis of fields and particles data suggests that Callisto may have a subsurface salty ocean that is responsible for a variable magnetic field induced by Jupiter's field. Callisto encounter C10 occurred on September 17, 1997, at an altitude of 539 kilometers. Data suggest that the internal structure of the Moon is not homogeneous, but partially differentiated, with a higher percentage of rock than ice having settled towards the center of the satellite. Callisto is probably less differentiated than the other Galilean moons. Galileo's last close encounter of its prime mission, E11, took place on November 6, 1997, at an altitude of 2,042 kilometers. The primary science objectives of this encounter included remote sensing of Europa's surface and Jovian atmospheric observations. Another objective was to obtain high-resolution images of 4 small inner Jovian satellites, Thebe, Metis, Amalthea, and Adrastea. Galileo's prime mission ended on December 7, 1997, 2 years after Jupiter arrival day. The orbiter showed no signs of quitting, so it was given new exploration objectives, defined in part by the findings of the prime mission. This new mission was called the Galileo Europa Mission, but its objectives also included Jupiter's other satellites, as well as Jovian fields and particles and atmospheric characteristics. This low-cost mission ran for slightly 2 years with a budget of only $30 million. The first encounter of the Galileo Europa mission, E12, occurred on December 16, 1997, at an altitude of 196 kilometers above Europa's surface. Instruments took stereo images of the Pule crater region. The stereo imaging discerned the topography of the region. The Connemara ice raft region was also observed. The high-resolution images showed crustal ice plates ranging up to 13 kilometers across, which have been broken apart and rafted into new positions resembling pack ice on Earth's polar seas. Galileo's magnetometer provided the strongest evidence of a liquid briny ocean on Europa. Data suggested that Europa's reversing magnetic field is induced by Jupiter's field rather than from the Moon itself. This could be explained by the existence of a saltwater ocean just under Europa's surface. The best theory is that tidal flexing generates enough heat to maintain a liquid European ocean. Once the existence of a subsurface ocean on Europa was suspected, the question arose, might life exist on Europa? The Moon meets the 3 main factors when searching for extraterrestrial life: water, organic compounds, and adequate heat. This does not prove that life exists there, only that it might. I do wonder what kind of big-toothed creatures are harbored in those dark depths. Encounter E13 occurred on February 10, 1998, at an altitude of 3,562 kilometers above Europa's surface. No remote sensing or magnetospheric data was collected because of a solar conjunction which reduced the capacity to transmit science data to Earth. Encounter E14 took place on March 28, 1998, at an altitude of 1,645 kilometers above Europa. Stereo imaging of Manan crater and the Tyre Macula dark spot was accomplished. Encounter E15 happened on May 31, 1998, at an altitude of 2,515 kilometers over Europa. The spacecraft carried out stereo and color imaging of the Cilix Massive, which data revealed to be an impact crater. Galileo also imaged near terminator maps of unexplored modeled terrain. Encounter E16 occurred on July 21, 1998, at an altitude of 1,830 kilometers above Europa. A spacecraft safing event prevented science observations. Debris generated in the slip rings between the spun and the despun section of the orbiter caused the safing event. Encounter E-17 happened on September 26, 1998 at an altitude of 3,582 kilometers in a southern polar pass that allowed observations of many of the targets missed during E-16. Galileo searched for evidence of large-scale shifting of surface features, which would indicate a possible liquid sublayer. The spacecraft imaged the Agenor Linea and the Thrace Macula region. Also imaged were the Libya Linea, a strike-slip fault zone, Rhiannon crater, Thynia Linea, and South Polar terrain. Radio science analysis of the Europan gravity field were made over a 20-hour period. Also, ultraviolet observations of Europa outgassing and atmospheric emissions were made. Encounter E-18 occurred on November 22, 1998 at an altitude of 2,273 kilometers. A safing event terminated science observations 6 hours before Europan closest approach. Encounter E-19 took place on February 1, 1999 at an altitude of 1,439 kilometers. Galileo carried out global and regional scale mapping along with the imaging of Tigid crater, Rhodmanthus Linea volcanic features, and mottled terrain. A safing event terminated science observations 4 hours after the Europan closest approach. Due to this, observations of Europa, Jupiter, and Io were lost. Encounter C-20 occurred on May 5, 1999, flying above Callisto at an altitude of 1,315 kilometers. Encounter C-20 began Galileo's Para-Jove reduction campaign. This involved incremental changes in the closest approach to Jupiter carried out over 4 Callisto encounters, C-20 through C-23. The campaign was designed to set up flybys of Io, the Galilean moon closest to Jupiter. Encounter C-21 took place on June 30, 1999 at an altitude of 1,047 kilometers. The near-infrared mapping spectrometer studied the trailing edge of Callisto. Also, dark surface material was imaged, and the PPR studied the equatorial region of Callisto. Encounter C-22 occurred on August 14, 1999 at an altitude of 2,296 kilometers. The spacecraft observed Callisto's ionosphere and measured the distribution of free electrons. Encounter C-23 happened on September 16, 1999 at an altitude of 1,057 kilometers. The spacecraft observed Callisto's ionosphere, measured the distribution of free electrons, and completed the Para-Jove reduction campaign. Galileo's second close encounter with Io, I-24, occurred on October 11, 1999 at an altitude of 611 kilometers. The spacecraft safed at 19 hours before the encounter due to a radiation memory hit. Galileo obtained valuable imaging of Io volcanism and observed a 10-kilometer-long eruption of Pele volcano. Io is the most geologically active body in the solar system, with more than 100 erupting volcanoes. Observing Io is the next best thing to traveling back in time to Earth's earlier years. Encounter I-25 happened on November 25, 1999 at an altitude of 300 kilometers. The spacecraft safed at 4 hours before the encounter's closest point of approach due to a software problem. But Galileo managed to collect dramatic pictures of Io volcanic activity and observed a mile-high lava fountain. The Europa encounter on January 3, 2000, E26, marked the beginning of the Galileo Mission. The spacecraft flew as close to Europa as 351 kilometers. Only limited observations were made during E26 due to factors such as the decreasing periods of Galileo's orbits, which allowed less time to develop orbital sequences, a smaller workforce and budget than during the Galileo Europa mission, and reduced downlink resources. Encounter I-27 flew by Europa on February 22, 2000 at an altitude of 198 kilometers. Galileo discovered volcanoes that changed from hot to cool since Encounter I-25. The spacecraft safed due to a transient bus reset. Encounter G28 occurred on May 20, 2000 at an altitude of 1,000 kilometers above Ganymede. Galileo's closest approach coincided with Cassini's closest approach to Jupiter while on its way to Saturn. Joint Galileo-Cassini observations revealed solar wind effects and magnetospheric dynamics. Also, high-resolution images of Ganymede were taken. Magnetometer data suggest that a salty water layer exists beneath Ganymede's icy crust. Encounter G29 occurred on December 28, 2000 at an altitude of 2,321 kilometers above Ganymede's surface. Real-time data was transmitted as Galileo flew from the inner magnetosphere through the magnetopause and bow shock and into the solar wind. Also, remote sensing instruments targeted Jupiter, its rings, and the Galilean satellites. Encounter C30 occurred on May 25, 2001 at an altitude of 138 kilometers above Callisto's surface. The spacecraft observed the Asteroid, Bahia, and Brand craters in the closest flyby to date. This flyby would set up an Io encounter in August 2001. Camera problems were possibly due to continued radiation exposure that affected distant images taken of Io. The camera problems were corrected before the closest approach to Callisto. A conceptual study, Human Outer Planets Exploration, proposed a surface base on Callisto to produce fuel for further exploration of the outer solar system. Callisto has the advantages of resources, a possible subsurface ocean, low radiation, and a strategic location. Encounter I-31 occurred on August 5, 2001 at an altitude of 200 kilometers, taking a north polar path above Io because magnetic readings above the pole might help to reveal whether Io generated its own magnetic field. Initial interpretations of I-31 data suggest that either the moon did not have an internally generated field or it was extremely weak. The Tavistar volcano was quiet, but a new eruption from a previously unknown volcano 600 kilometers away was spreading the tallest plume yet observed, 500 kilometers above Io's surface. Fortuitously, Galileo's flight path took it through the outskirts of this plume, and the Plasma Science instrument detected particles that had erupted from Io's interior only minutes earlier. Galileo detected tiny sulfur dioxide snowflakes of 15 to 20 molecules each. The snowflakes formed as hot gases from the vent rose through Io's frigid, thin atmosphere and condensed. During Encounter I-32 on October 15, 2001, Galileo passed closer to Io than ever before, only 181 kilometers above the moon's south pole. The spacecraft made observations of several volcanic areas, as well as a new hotspot and plume eruption in the Moon's southern region discovered during flyby I-31. Magnetic field measurement findings implied a model in which Io's iron core is heated from the layers around it rather than being heated from its center. Encounter I-33 was the closest and last flyby that Galileo performed past any of Jupiter's 4 major moons. The spacecraft cruised to within 102 kilometers of Io's surface on January 17, 2002. The close encounter gave Galileo the gravity assist necessary for it to end its multi-year mission, putting Galileo on a ballistic trajectory for an impact with Jupiter in September 2003. The spacecraft's propellant nearly exhausted, mission scientists wanted to avoid the small chance that a crash into Europa could contaminate it with Earth microorganisms. Plans for science observations did not go as hoped. 28 minutes before closest approach, the spacecraft placed itself into safe mode. This caused the craft's cameras and instruments to stop taking data and await further instructions from Earth. The safing incident probably resulted from the radiation environment near Jupiter. On November 4, 2002, during encounter A34, Galileo flew closer than it ever had to Jupiter and Amalthea. Galileo flew as close as 160 kilometers to Amalthea. Data from the encounter helped to determine the mass and density profile of the small moon. Amalthea's low density suggests a highly porous rubble pile or low density rock or a rock-ice mixture. Just after the encounter, Galileo's tape recorder failed to play back the data collected. The problem was not a stuck tape, as before, but the result of radiation damage to one or more of the instrument's infrared LEDs. To correct the problem, JPL would send commands to initiate electric currents to pass through the LEDs. It was believed that these currents would return some of the LED atoms to their original locations in their crystal lattices. After multiple electric current applications, the tape recorder began running again and downloaded its stored data. Galileo's final orbit, J35, took it on an elongated loop away from Jupiter, from which it returned on September 21, 2003, to plow into Jupiter's thick atmosphere. The spacecraft disintegrated in Jupiter's dense atmosphere at 11:57 a.m. Pacific Daylight Time. However, the Deep Space Network did not receive the craft's last signal until 12:43 Pacific Daylight Time due to the time delay for the signal to travel to Earth.